Hi, I'm Tim, the Director of Art for Pixelmatic. Recently, I took on the task of improving the visuals of the planet shaders for our game Infinite Fleet. This included making them more detailed, more flexible, and fixing a handful of technical problems that existed in the early versions. Of particular note is the shader for our planet atmospheres. Updating this shader involved some problem solving that I thought was interesting enough that I wanted to make a video detailing the problem and how I solved it. The shader is based on the dot product of the atmosphere's shell, which on its own creates a radial gradient. This base gradient was then used to sample from a different gradient to remap its values to make the atmosphere more concentrated around the very rim of the planet. This was easy to set up, but was inflexible as the remapped gradient can't be converted into an exposed property. A bigger problem, though, was that the fall-off effect was very sharp as the transition between two values in this gradient editor is always linear. This made our atmospheres look almost like they had a hard edge, which is undesirable. My solution was to split the dot product into two parts based on a threshold value. Whenever the dot product was less than this threshold, a certain exponent would be applied to make the gradient fall off smoother. Whenever it was larger than the threshold, a different exponent would be applied. Being able to apply a high exponent to this gradient makes the fall-off very soft, which is the look we're going for. This introduced a new problem though. One parameter we want to be able to control is the atmosphere thickness, which is done through simple displacement of the sphere geometry. Whenever this is changed though, the dot product threshold value needs to be updated so that the atmosphere rim stays in line with the outer edge of the underlying planet. While it's easy to change this manually, this shader will eventually be used in combination with our procedural generation system, so the change will need to be handled automatically. The challenge is that there isn't an obvious relationship between how the threshold value should change and how much larger the atmosphere displacement gets. The relationship isn't linear, it isn't quadratic, nor is it cubic. Given that the threshold value can never quite reach 1, since that would require the atmosphere to be infinitely larger than the planet, it would seem to be a tangent formula, but simply putting a tangent or arctangent node into the shader graph isn't sufficient. The player will potentially get very close to the planet's surface, so any minor offset may be noticeable. The formula for determining this threshold value, then, has to be perfect. So how did I figure it out? Let's take an alternate visualization to figure out exactly what it is we're trying to accomplish. Remember that this shader does not incorporate any kind of volumetrics. There isn't really a haze around the planet. It's just a customized radial gradient mapped onto the atmosphere shell to mimic the appearance of a glowing haze. Let's remove the inner and outer glow to make this easier to visualize. What we're after is this ring, specifically what dot product value between the view vector and the sphere's surface normal will get us this ring. Since we're only going to be using a single value for the entire atmosphere, we can simplify this to two dimensions, and what we have are two circles. The ring we're trying to generate has to be horizontally in line with the inner circle, and what we're after is this vector, going from the center of the circle to this intersection point. Moving in a bit closer, if we draw a vertical line from the top of the inner circle down, we get a right triangle. We know the vertical line is the radius of the planet, and that the hypotenuse is the radius of the planet plus whatever our displacement value is for the atmosphere. What we want to calculate is this angle theta. Since this is a right triangle, we can calculate the longer leg's length using the classic Pythagorean theorem. Since we know the length of every side, we can calculate theta using the law of cosines. Knowing the angle isn't quite good enough. What we really want is the direction of the hypotenuse. Thankfully, that's fairly easy to figure out. If we consider this whole diagram to be on a coordinate grid, then we can think of the direction of the hypotenuse as its slope, which we can get by taking the tangent of theta. That gives us the vector of the hypotenuse. All that's left is to get the dot product between that vector and the horizontal vector, and that will give us the threshold value we need. Now I just convert all of this trigonometry into shader graph nodes, and the atmosphere shader works flawlessly. We can update the thickness of the atmosphere to any value we want, and the glow of the rim will always perfectly line up with the outer edge of the planet. Thanks for watching.